Hello everyone. So today we'll be solving this LeetCode medium problem. Stable subarrays with equal boundary and interior sum. So the problem is like self-explanatory from the problem name itself. But let's see the problem statement. So we are given an integer array capacity. Now we define the subarray capacity as stable if its length is at least 3 and the first and last elements are equal to the sum of elements strictly between them. That is, capacity of L should be equals to capacity of R, and the elements present between them the sum of them should be the same as these values. That is, capacity of L is the same as capacity of R, as well as the sum of values that lie between them, that is capacity of L plus 1 till R minus 1, they should have the same sum as capacity of R and capacity of L, and the length should be at least 3 so that this middle segment exists. For example, if length was 2, then for 0 1 there exists no value in between. Hence this is why this condition is given separately, that length should be at least 3 so that we can have some middle segment and find its sum. Now we are given this integer capacity and we need to find the number of stable subarrays in the given array, and like the length of array can go up to 1e5. So like going through all the possible subarrays will obviously give us TLE. So let's see the given input. So we first need to check, means we need to find points such that they are, means we have two equal points at certain positions, right? Then only the capacity of L and the capacity of R remains the same. So here we can see like this 9 exists twice. So these are like 2 points, and we can see like the length that of the subarray that will be forming is greater than equals to 3. So let's try to see whether this subarray is stable or not. So as you can see, the internal sum of this subarray is 9, which is equals to capacity of L as well as capacity of R. So hence this will be a valid subarray. Now let's see for 3. So since 3 exists at this point and this point, okay, so let's see the internal sum. So internal sum here is also 3. So hence we can also see that this subarray would also be valid. So hence total number of subarrays that is stable here is 2. There exists no other subarrays. For example, we have 3 3 3. So if we pick this subarray, then we see like its length is less than 3. Okay, so we will not count this. So it means account those points which are, means if a value x exists at multiple points, so we will be looking through those pairs of x's such that their length is greater than equals to 3, and then only see the internal sum. Okay, so in this case the output was true. Let's see another input. So we have 1 2 3 4 5. As we can see, like there exists no x which is, means frequency is greater than 2, frequency is greater than 1. So there exists no x, so we cannot form a pair of L comma R such that capacity of L is the same as capacity of R. Hence the output here is 0. Then in another test case we have like -4. So this -4 exists at two places. So let's see whether the inside sum is -4 as well or not. As you can see, 4 minus 8 is -4 indeed. Hence this will again be a valid subarray, valid stable subarray. Then we see like all other elements does not exist greater than 1, but this 0 exists more than 1 times. But for this 0 0 we see like this is equals to this, but there exists no internal segment because the length is 2, and we only need to account the length of subarray is greater than equals to 3. Hence in this case also this will not be a valid subarray, valid stable subarray, and hence the output here is 1 only. The entire array is the stable array. So what will be the most naive approach of approaching this problem? It will be to consider all subarrays whose length is at least 3. So we'll simply account through all subarrays. So let's define the starting point of subarray as L, which will move from 0 till L minus 1. And now this right point can only start from, if we have a L, it cannot start from L plus 1 because it will make a subarray of size 2. So it should start from L plus 2. Right, then only we'll have at least a subarray of length 3. So we'll start this R from L plus 2 till N minus 1. Now the subarray that we have from L to R, we need to see whether the capacity of L is equals to capacity of R, and what do we need to see? We need to see whether the sum between them is the same as this value or not. Now when we now we see that we need to like find the sum of a range of the array. So we need to find sum of range of array. Okay, so these like L and R will be changing, and will definitely need to find their internal sum multiple times, right? Because as L and R changes, we need to be able to find this internal sum in some efficient way, right? Because obviously we have utilized big of n square. So if we try to like simply iterate through from L plus 1 till I minus 1 and then find, then it will be of the order of n cube. Okay, so how like we can move from n cube to means optimizing this getting of sum. So we obviously know that whenever we want to like find the range sum in like constant time, then we usually use the concepts of prefix sums. So I hope you are aware of what a prefix sum is. I will be telling you. So what a prefix of I is, suppose we have a prefix of I, so it simply denotes the first I elements. First I elements. Okay, that means we only consider the array from the index 0 till I, and this prefix of I will denote the sum of ARR 0 plus ARR 1 till ARR of I. Okay, so this is like the prefix of I, what it will be. So how we'll be computing it? So initially let's mark it the prefix of 0 as ARR of 0. Now this prefix of 1 will be simply what? The prefix of 0 plus ARR of 1. So ARR 1 plus prefix of 0. Then what prefix of 2 will be? It will be simply the sum till this value plus the new value that we have got. So it will be simply prefix of 1 plus the new value that we have got. Okay, so we can see like prefix of I is simply what? It is simply prefix of I minus 1, means the sum of values till I minus 1th index plus the value that we have gotten at the ith index. Now if this means prefix value is already calculated, that means we are able to get the sum of values till the ith index using this prefix array. Then if we want to find the sum of elements in the range L to R, then it will be simply what? It will be simply the sum till, means from 0 till R, so it will be simply prefix of R, and from this we need to delete this segment, right? So we need to remove this segment, so it will be simply, we'll remove this prefix of L minus 1. So if you want to find the sum of range of elements in L to R, it will be simply prefix of R minus prefix of L minus 1. So if we have already calculated this prefix array, then what is our goal here? The goal is to calculate the sum of elements in the range L plus 1 till R minus 1, right? And what it is? It is simply prefix of right term minus prefix of left term minus 1. So it will be prefix of right term minus prefix of left term, which is L plus 1 and minus 1. So minus 1. So it will be this. So it will be what? Prefix of R minus 1 minus prefix of L. Okay, so at each step we'll simply find this value and see whether this value is the same as capacity of R, and hence in the brute force manner we'll be able to see for each possible greater than or equals to length 3 subarray whether the array is stable or not. So I hope you are able to like you are aware about prefix sums, and if you are not, now you know how you will be using it to find range sums in like normal array, non-updating array, and then we'll be able to calculate this in this n square approach. So let's see the code as well to get a better understanding. So we simply create this prefix sum with long because the range of elements can go up to 1e9. So 1e9 into 1e5, the maximum sum can go till 1e14. Okay, so hence we have taken this value as long so that it means it does not give us integer overflow. Now what we do, we at each I, the prefix of I will be capacity of I plus, if this I is greater than 0, that means we will simply add prefix of I minus 1. Okay, now once this is calculated, we need to find the number of stable subarrays. So we initialize this with 0 and we have it long because the array can go up to 1e5. So the number of 3 length subarrays will be like what it will be? It will be n into n minus 1 of the order of n into n minus 1, means we remove the two length subarrays, which will be n minus 1. So minus n minus 1. Okay, so we simply remove it, so it will be like order of 1e10 maybe. So this is why it may go up to long now, hence we have the result is stable as long now. Now what we'll do, we'll check whether this capacity of R is the same as capacity of L, as well as the formula that we have gotten, that is the means for L to R, whether the sum from L plus 1 to R minus 1 is the same or not. And we are calculating this in constant time using this prefix array by finding out prefix of R minus 1 minus removing this prefix of L. Okay, so on prefix of R minus 1 we are removing this prefix of L part, so that only this part remains. So if this part is the same as capacity of R, that means the subarray from L to R is stable and will simply increase the stable count. Okay, so this will be like the big of n square approach, and as we know, like n can go up to 1e5, so this will obviously give us tail. Hence we need some means optimizations here, or like more pre-computations. We need to do some more pre-computations to like further optimize it. So like whenever we need to solve some problem which has given a particular formula, then we definitely try to rearrange the formula to see like whether we are able to get the result in terms of a single index only. This is what we have learned, because we have solved various problems related to the same concept, where if we are given a formula, then we try to rearrange it so that it only becomes in the form of a single index. Okay, and then on the basis of that particular single index, we need to means account the number of values that have occurred so far. Okay, so let's try to rearrange the formula that we have. So what do we have here? So we have capacity of L is same as capacity of R, as well as what do we have? We have prefix of R minus prefix of R. Sorry, it is let's remove it. So it is prefix of R minus 1 minus prefix of L is same as capacity of R. Okay, so what do we want? We want the terms to be in the form of prefix of R minus 1, and this is prefix of L. It is the same as capacity of R. That means, and what do we want? We want the terms to be in the form of a single index only. So we want the formula such that it is on the form of single index. So let's try to put these R minus 1 and R together. So then we'll get prefix of L is the same as prefix of R minus 1 minus capacity of R. Okay, this is what we get. So hence, if we are at a particular index R, then what do we need to find? We need to find this value, prefix of R minus 1 minus capacity of R, and then the number of prefixes that we had with this value, means the L that we had. Hence there can be multiple places where we have encountered this value so far, means maybe at this place, then this place, then this place. Okay, so all of these will be forming a stable subarray. All of these will be forming a stable subarray if and only if this condition is also satisfied. Means along with this prefix of R minus 1 minus cap of R, this condition is also satisfied, that the capacity of L is the same as capacity of R. Okay, so what do we have find? We need to means check for two conditions at once. We need to see that this capacity of L is also exist, as well as this prefix of L is also matched. So we need to find the number of occurrences of this value on the left side, and this prefix of L is simply prefix of R minus, it is prefix of R minus 1 minus capacity of R, and this capacity of L is simply the capacity of R only, because it is the same. So we need to find the number of pairs that we have already encountered on the left, which is of the form capacity of R and prefix of R minus 1 minus capacity of R. Why we are seeing it as a pair? Because we need to satisfy both of these conditions. Hence, to satisfy both conditions, these two values should exist as a single entity, right? Because even if we have a capacity of R and some prefix of L dash, okay, so that will not be a valid answer, right? And even if we have the prefix of L, but we do not have like capacity of R dash we have. So even if we have this prefix of L on the left, if we do not have the value as same as capacity of R, then that will also not be a valid answer. Okay, so hence we need to satisfy the both of the requirements. Hence we need to see the number of occurrences on the left which satisfy capacity of R as well as prefix of R minus 1 minus capacity of R. And we know, like, whenever we want to like find out the number of values on the left which has a value requirement which we want to find, so we'll be using hashing concept. Okay, so hence generally whenever we have prefix sums or calculations concept and we want to count something, count number of something, something, then we generally use prefix sums. Once prefix sum is there, and plus we use hashing, so that we are means keeping track of the frequencies of these unique pairs that have encountered so far. And for a particular L, for a particular R, what we'll do, we'll simply update our stable count by this map. Means we'll create means keep the track of the frequencies of these. So we'll simply, like, suppose we have created a map, so we'll keep track of capacity of R as well as prefix of R minus 1 minus capacity of R. Okay, so this will be like this will be the approach to solve these kind of problems. Like, this is pretty standard now. Whenever we are given a formula, we try to rearrange it and then try to bring it in the form of a single variable only, and then for a particular R or for a particular L, we try to find, means see the occurrences on the left or on the right based on our requirements, as you can see. And here it was on the basis of R, we wanted to find out the number of values which has occurred so far on the left, and for that we'll be using obviously the same map and the same concepts that we have used of prefix sums plus hashing. So this, like, we know, like, we need to store, means we need to create the map in the form of the key will be pair of int comma int because it is a pair, and the count will be int. So as you can see, like, since this is like this key is not a simple integer, hence we cannot use unordered map here. I hope you are aware, like, using unordered map with this key is not possible. Why? Because, means if this key is simply not means anything other than integer, string, character, you can see the normal values, the means the key values allowed for unordered map, because the internal implementation of unordered map is in such a way that hashing of, means these simple data types is possible, but hashing of these complex data types is not possible. Okay, so hence we'll be simply using a normal map of pair of int comma int comma int. Okay, and so we'll be using this, and then we'll try to solve this problem. So yeah, let's see the code as well, so that the approach gets in our mind. So we'll be using the same concept to create, means calculate the prefix sums. Now what do we wanted? We wanted prefix of R minus 1 minus prefix of L equals to capacity of R. So we write it in the form of prefix of L, so it becomes prefix of R minus 1 minus capacity of R. So we need to find the number of values on left which has the same value as prefix of R minus 1 minus capacity of R, as well as this constraint should also be satisfied that capacity of L is equals to capacity of R. Since we create a simple map of this capacity as well as this prefix value. So we create this prefix value. Now we also need to make sure along with that the prefix length should be greater than or equals to 3. Hence, if we are at a particular R, then we should not have added the contribution of R minus 1 in our map till now, because this will create an array of length 2. So at each step we'll be adding the contributions of this R minus 2 in a late form of basis. Okay, so when we are at a particular R, so we'll, for length 3, since we want length 3, so we can start the R from R equals to 2. Now for the R equals to 2, we want the contribution till R minus 1, right? We want the contribution till R minus 1. We do not want the contribution of R minus 2 because that will create a 2 length subarray. Okay, so hence we'll be inserting into map in like a late form because we want to avoid the subarray equals to 2 condition. So we'll be using this logic of putting R minus 1 at each R. Hence for a particular R, we'll have all the prefix means occurrences from 0 till R minus 1, and this R 0 till R minus 2, and this R minus 1 will not be there. Okay, so Let's see the code as well. So we have the same variable stable. Now we start from r equals to 2. The index r minus 1 now becomes a valid start point. Okay, so we'll simply add this to our means map. So it will be capacity of r minus 2 and prefix of r minus 2, and we'll increase the count. Now the requirement, prefix requirement currently is prefix of r minus 1 minus capacity of r, as well as we want the same, means capacity of l should be same. So we need to find the pair capacity of r comma prefix requirement. Okay, so we see whether it exists in map or not, and if it does, then we'll increase our stable count by the number of times it occurs on the left, and we'll simply return the stable count. So this will be like the overall approach for this problem. And as you can see, like we have initially created this prefix sum vector as well as this map. So the space here would be of the order of n, and at each step what do we need to find? We need to find the number of occurrences of this pair, particular pair. So it will be of big of log n. This map will be taking big of log n, and since we are traversing through n, so the overall complexity will become n log, and n here is 1e5. So 1e5 into log n, which is like approximately 1e6, so which will be acceptable within time limits of 1 or 2 seconds. So let's try to submit the code as well and see like how well it performs, and how much time does it takes to run. So it runs in 280 ms, which is fine. Now let's try to see whether like this key is allowed or not. Okay, this key is allowed in unordered map or not. Let's try to see. And as you can see, like this key pair of int comma long long is not allowed, because in the internal implementation of unordered map, we try to create hashes of the keys that we have, and hashes of simple keys like integer, string, boolean, these are means possible, but hashing these complex data structures is not possible. Hence we try to use a simple map whose internal implementation is done using red black tree, where we do not need to create hashes. So hence like we simply avoid that disadvantage of another map in the map concept. Okay, so that's why we are able to use this as a key in map and not able to use it in another map. You can also like read about it online on how the hashing works in another map. So I hope like you were able to follow along with the approach, the brute force algorithm, as well as the optimized one. And like from like till now we have solved multiple problems related to prefix sums plus hashing, where we need to count some number of stable subarrays, or this means just this formula keeps changing, and everything else, the entire concept remains the same. We simply, for a particular index that we are currently on, we try to convert the formula on the basis of this particular index, such that we are able to find the values that we are required on the left, and we simply store their frequencies in a hash map. So this is like a pretty popular approach that can be used to solve a lot means a very wide range of problems. So I hope like you were able to like grasp the concepts and will be able to utilize this approach in solving similar problems in future. And if you did, like make sure to like, and if you have any doubts remaining, feel free to comment down and I will be happy to help. Thank you so much for watching.